Today we are going to design an axially loaded column. I am George Kamiti and this is George Kamiti e-learning platform. The question is, a proposed 5-meter long internal column in a rigid jointed steel structure is to be loaded concentrically with 1000 kilonewtons dead and 1000 kilonewtons imposed load as shown in the figure below. Assuming that fixity at the top and bottom of the column gives effective rotational restraints, design column sections assuming the structure will be A, braced and B, unbraced. So we got a diagram that is showing a column in between two floors loaded with 1000 kilonewtons of dead load and 1000 kilonewtons of imposed load. So let's see how this structure will be designed. Thank you. So starting with the braced column, the first step will be calculation of the design axial loading. And in this case, the factored loading, that is FC, will be given by this formula 1.4 GK plus 1.6 QK, where GK denotes the dead load and QK denotes the imposed load. And therefore, FC, the factored loading, will be given by 1.4 times 1000, which is the dead load. We add this to 1.6 times an imposed load of 1000 kilonewtons. So this is going to give us 1.4 times 1000, which is 1400 kilonewtons, plus 1.6 times 1000, which is 1600 kilonewtons. When we add, we are going to have 3000 kilonewtons, and therefore the factored loading FC is equals to 3000 kilonewtons. Then from there, we are going to determine the effective length of this column. And therefore, step number 2, determination of the effective length of the column. And effective length is usually denoted by LE. For the braced case, the column is usually assumed to be effectively held in position, and therefore the effective length will be given by 0.7 times the length of the column. Therefore, the effective length is going to be 0.7 times the length of this column, which is 5 meters. That's going to give us an effective length of 5 meters. Therefore, effective length is equals 3.5 meters. Then step number 3 will be section selection. So we go to step number 3, section selection, where we are going to select a suitable UC section. But in this case, we can only do it by trial and error method. And we are going to try this section. Therefore, the initial trial, we are going to try this UC section with a serial size of 254 by 254 by 107 universal column. This section have got a design strength, or the design strength of steel 265 newtons per square millimeters. It has a radius of gyration about the minor axis, that is about the YY axis, of 65.7 millimeters. The gross cross-sectional area of the section is 13,700 square millimeters. The local buckling for the flange, that is B over T, is 6.3, and that for the web, which is D over T, is that is 15.4, and therefore the slenderness ratio will be given by effective length divided by the radius of gyration about the y axis. And in this case, we have the effective length, which is 3.5 meters. Convert to millimeters, multiply this by 1,000, which is going to give us 3,500 millimeters. We divide by the radius of gyration, which is 65.7 millimeters. Therefore, 67.5 millimeters. And this is going to give us a slenderness ratio of 53. So the slenderness ratio is 53. So we are going to use this slenderness ratio to determine the compressive strength of steel, and that information we are going to get it from table 24C of the BS 5950. And from that table, that is table 24C, when the slenderness ratio is 53, the compressive strength of steel is going to be 208 newtons per square millimeters. Therefore, we have 208 newtons per square millimeter being the compressive strength of steel. And therefore, since the ratio of B to T is 6.3, and we know that B over T should be less than 15 times a constant, and this is all about classifying our section that we have selected, classifying our section so that we know whether this column is a slender column or it is not a slender column. And therefore, using this formula, B over T less than 15 times a constant E, and remember this constant is given by, so we are going to have 15 times, the constant is usually given by 275 divided by Py raised to the power of 0.5, or in other words, just calculating the square root of 275 divided by Py. And in this case, we are going to have 15 times 275 divided by Py, which is 265. Py is the design strength of steel, which is 265. That's what we are working with. Then this one is raised to the power of 0.5 is 15.28. So when we compare with B over T, which is B over T, we have it as 6.3. You find that 6.3 is actually less than 15.28. The other comparison will be comparing D over T, and in this case, D over T should be less than 40 times a constant. And 40 times the constant will be 40 times the square root of 275 divided by Py, which is 265, and then find the square root of that, that is raising it to the power of 0.5. And that is going to give us 40 times that constant, we are going to have 40.74. And actually, D over T, which is 15.4, is less than 40.74. So this means that the UC column we have selected is not slender. Therefore, the UC, universal column, is not slender. Then from there, we are going to calculate the compressive resistance of this section that we have selected. Therefore, the compression resistance of this steel will be given by gross cross-sectional area of steel times the compression strength, the compressive strength of steel. And therefore, the gross cross-sectional area of this section is 13,700 square millimeters. Therefore, we multiply 13,700 times the compressive strength of this steel section is 208 newtons per square millimeters. So we multiply by 208 square millimeters, and then we divide this by 1,000 so that we can convert the compression resistance from newtons to kilonewtons. And when we do so, we are going to have a compression resistance of this steel of 2,850 kilonewtons. Therefore, when we compare PC and FC, we find that the compression resistance should be greater than FC, that is the factored loading. And in this case, you will find that the compression resistance, which is 2,850 kilonewtons, is less than the factored loading, which is 3,000 kilonewtons. 3,000 kilonewtons. And therefore, this means that the section we have selected is not okay. It is not okay. We are going to select another section, or we are going to try another section. Remember, we said that this column design can only be done by trial and error method. Therefore, let's try our second section. So, you can say second trial. And in the second trial, we are going to try 305 by 305 by 118 universal column, that is UC. And from the BS 80 and from the BS 5950, the design strength of steel for this section is 265 newtons per square millimeters. The radius of gyration about the YY axis is actually 77.5 millimeters. Then from there, the gross cross-sectional area of this section is 15,000 square millimeters. Ratios for local buckling, B over T for the flange, that is 8.2, and that for the web, that is B over T, is 20.7. Therefore, that is the information that we are getting from BS 5950 for this column section. So from there, we are going to calculate the slenderness ratio. And in this case, the slenderness ratio for this section will be given by effective length divided by the radius of gyration. And the effective length for this section is 3.5 meters. Converting to millimeters, we multiply 3.5 by 1,000, which is going to give us 3,500 millimeters, divided by the radius of gyration, 77.5 millimeters, 77.5 millimeters, and that is going to give us a slenderness ratio of 45. So we are going to use this slenderness ratio of 45 to determine the compressive strength of this steel section. And this information, we are going to get it from table 24C of the BS 5950, table 24C of the BS 5950. And from the BS, the compressive strength of this section with a slenderness ratio of 45 is going to be 222 newtons per square millimeters. Therefore, that is the compressive strength of this steel section. And therefore, the compressive or compression resistance of this section will be given by its gross cross-sectional area times the compressive strength of this steel section. And therefore, the gross cross-sectional area is 15,000 square millimeters. So we are going to have 15,000 square millimeters times PC, which is 222 newtons per square millimeters. And for us to be able to get the answer in kilonewtons, we are going to divide by 1,000. And therefore, the compressive resistance of this section is going to be 3,330 kilonewtons. So that is the compression resistance of this steel section. And therefore, as we said, the compressive resistance should be greater than the factored loading. So we can see that this compressive resistance of 3,330 kilonewtons is actually greater than the factored loading, which is 3,000 kilonewtons. And therefore, it means that the section we have selected is very much okay. The section we have selected is okay. Therefore, that is how we go about it when the column is braced. Then after carrying out the calculations for the braced column, we are going to check the unbraced column. That is when the column is unbraced. Unbraced column. So for the unbraced column, its effective length, the BS 5950 states that the effective length will be given by 1.2 times the length. That is when the column is unbraced. Therefore, the effective length for this for unbraced column is going to be 1.2 times the length of this column, which is 5 meters, and therefore that is going to be 6 meters. Therefore, the effective length for unbraced column is 6 meters. Then from there, we are going to select a suitable section. Therefore, section selection, and in the same way as we did for the braced one, we are going to use the trial and error method. Therefore, we are going to have a first trial, and our first trial is going to be a column with this serial size 305 by 305. Let me write it down here. 305 by 305 by 158 universal columns. So that is the section we are going to try. And from the BS 5950, that is Appendix B, the strength of steel is 265 newtons per square millimeters. The radius of gyration for this section is 78.9 millimeters. The gross cross-sectional area for this section is 20,100 square millimeters. The local buckling ratio for the flange, that is B over T, is 6.21, and that for the web, that is D over T, is 15.7. Then the compression resistance for this section will be given by its gross cross-sectional area times its compressive strength. And therefore, for us to be able to get the compressive strength for this section, we are going to calculate the slenderness ratio. And slenderness ratio will be given by effective length divided by the radius of gyration. And in this case, the effective length is 6 meters, which when we convert to millimeters, we multiply by 1,000, is going to give us 6,000 millimeters divided by the radius of gyration, 78.9 millimeters. And that is going to be 76. Therefore, from table 24C, of the BS 5950 with a slenderness of 76, the compressive strength of steel is going to be 165 newtons per square millimeters. So that is the compressive strength for this steel section. Therefore, the compression resistance will now be given by gross cross-sectional area of the section, which is 20,100. Therefore, 20,100, we multiply this by the compressive strength, which is 165, and then we divide by 1,000, which is the same as 10 raised to the power of -3, for us to get the PC in kilonewtons. And when we do so, we are going to have a compressive strength, or a compressive resistance, of 3,317 kilonewtons. So when we compare this with FC, we will find that 317 kilonewtons is greater than FC, which is 3,000 kilonewtons, and therefore it means that the section we have selected is okay. So that is when the column is unbraced. Therefore, that is the end of our today's video, and we thank you for your support. Thank you for watching. Please, if you are not yet subscribed, consider hitting that subscription button as well as the notification bell so that you'll be notified when we upload every video.